Assalamualaikum warahmatullahi wabarakatuh. Good morning, Dr. Zuraidah Kusaimi and Dr. Nurlaidi Ahmad. My name is Muhammad Adiputra bin Armain and I am delighted to welcome you to today's FYP presentation on a review on synthesis methods for producing black TiO2 and its photocatalytic performance. Due to its accelerated oxidation process (AOP) and strong photocatalytic activity, TiO2 is frequently employed in environmental remediation. Conventional TiO2 nanopowder has quick recombination and poor quantum efficiency, limiting its solar energy harvesting potential. Today, we will investigate black TiO2. Black TiO2, exceptional photocatalytic efficiency and visible light spectrum applicability are increased by flaws in the Ti4+ lattice and Ti3+ ions. We will examine black TiO2 production techniques and their effects on crystal structure, morphology and optical characteristics which influence the photocatalytic activity. Start with the issue statement that drives our black TiO2 production and photocatalytic study. TiO2's 3.2 eV band gap limits its solar energy efficiency. TiO2 can only absorb UV energy, which is less than 5% of the sun spectrum. Thus, TiO2-based photocatalysis cannot use more solar energy. To harness visible light, a large percentage of solar radiation, TiO2 must be modified. Black TiO2, a unique variety, causes flaws in the Ti4+ lattice, forming Ti3+ ions. These flaws absorb visible light, increasing photocatalytic activity. Black TiO2 is promising, but our grasp of its production processes is lacking. The literature lacks comparative studies on diverse synthesis methods, their circumstances and their effects on black TiO2's crystal structure, morphology and optical characteristics. This information gap prevents us from optimizing synthesis process and fully using black TiO2's photocatalytic potential. After defining the issue, let's discuss our study goals. Objective 1. Compare black TiO2 synthesis. We initially investigate black TiO2 production techniques, metal reduction, CaH2 reduction, hydrogenation, electrochemical reduction, vacuum annealing and modified sol gel are examples. We seek to find the most efficient and effective way to make high quality black TiO2 nanoparticles by researching the impact of each synthesis pathway on its crystal structure, shape and optical characteristic. The second objective is to assess black TiO2 photocatalysis. After synthesizing black TiO2 using diverse ways, we will test its photocatalytic performance. We will rigorously test black TiO2's ability to degrade organic contaminants under visible light irradiation. We want to find the best black TiO2 production technique by comparing photocatalytic activity. First synthesis method is metal reduction. It's the summary of extract data analysis that I already extracted from the journal paper that I reviewed. The element in the table is the morphological structure, source of TiO2, reaction condition, research focus, post-thermal temperature and time, and crystal phase. I will focus more on the morphological structure and the crystal phase. So in the metal reduction method, as we can see in the image, figure A shows the nanotube structures are equally dispersed over Ti foil and vertically aligned with a regular and highly ordered morphology. This is the original TiO2 before the annealing process. After annealing with the different temperature of 300 450 and 600. As we can see in the figure B, C and D, nanotube array structure was well preserved after annealing, indicating that the study's heat treatment did not affect their morphology. The XRD image examines the black TiO2 nanotube arrays annealed at various temperatures for crystallinity and phase composition. The figure shows that the black TiO2 nanotube arrays were extremely crystalline and had identical diffraction peaks to anatase TiO2 reflection per lens. This XRD diffraction pattern showed a Ti diffraction peak, perhaps due to Ti sheets underlying the B black TiO2 nanotube base. Second synthesis method is CaH2 reduction. Morphological structure confirm there is decrease in TiO2 morphologies. The well-resolved lattice features in the image reveal that the original TiO2 nanocrystal are strongly crystallized. Typical for anatase, pure and reduced TiO2 have 0.35 nanometer lattice spacing. After the CaH2 reduction, the titanium nanocrystal has a crystalline core and a 2 nanometer thick disordered surface layer in the figure. The XRD shows that the CaH2 uses the retail phase of mixed anatase retail degussa P25 sample. After the CaH2 lowering, the IR decrease. The third step is hydrogenation. Morphological structure in this step that after the hydrogenation in figure A and B, it shows no notable surface morphologies. In figure C, the TiO2 nanorods with average diameter of 150 nanometer and length of 1.8 micrometer cover the whole FTO structures. And the result in XRD patterns before and after the hydrogenation, it shows no phase shift following the hydrogenation, whereas TiO2 peak intensity reduces. In hydrogenated TiO2 investigation, its defects density increase. The fourth synthesis method is electrochemical reduction. The morphological structure in the photos illustrate prepared sample integrity nanotube morphology. In the figure A to C, the black TiO2 nanotube decreased at various voltages were well arranged with approximately 90 nanometer pore size and grew parallel to the electric field. Negative 10 volt black TiO2 nanotube exhibited the greatest surface quality. The negative 20 had mild damage and negative 40 showed evident destruction in the red dotted block. Hence, current corrosion caused nanotube to lose a modest quantity of TiO2, damaging the surface shape. XRD image, we can see the nanotube composition and crystal structure. All samples had Ti diffraction peaks, and both annealed and reduced nanotube displayed strong diffraction peaks corresponding to anatase photo, indicating that the black TiO2 nanotube retained their crystal structure following electrochemical reduction. Synthesis method is vacuum annealing. The morphological structure in the illustration shows that the nanocomposite sphere with uneven edges and aspect ratio 1.04. Increased annealing temperature was thought to have changed the nitrogen-doped white TiO2 nanocomposites, elongated form to spherical. And in the XRD, we see that the crystalline size of black titanium was observed to be larger compared to the white TiO2 due to the high annealing temperature used during the synthesis process. The last synthesis method is modified sol gel method. In the morphological structure, we can see that the TiO2, black TiO2 were irregular in shape and agglomerated, and the crystal phase shows that it is crystalline in nature and in anatase phase. Now, we will review the photocatalytic activity of different synthesis method of black TiO2. The first synthesis method, which is aluminum reduction, the material produced is pure black TiO2 produced at different temperature. Here we can see that it is used for production of hydrogen gas. It is 1.7 times higher than the hydrogen produced in pristine TiO2. Next is the CaH2 reduction method. The materials produced are black TiO2 nanotube arrays. It is used for photocatalytic CO2 reduction to CO. And black TiO2 produced here demonstrated yield of 185.39, which was more than 3 times as much of TiO2 nanotube arrays. And the third method is hydrogenation. The materials is hydrogenated TiO2 nanorods array. It's used for photoelectrochemical sensor for organic compounds under visible energy. The next step, which is the chemical reduction, the material produced is AU loaded black TiO2 nanotubes. It is used for visible light photocatalysis, and it shows that the AU black TiO2 nanotube existed in decomposing the active 2% of RHB in 60 minutes, which was approximately 8 and 2 times as much as the degradation efficiency of TiO2 nanotube, which is better. Next, state of annealing, the material is nitrogen doped black TiO2. It is used for production of hydrogen gas, and the production of black TiO2 is 4 times higher than white TiO2. Moreover, the photocatalytic activity of black TiO2 shows a 34% increase due to the effect of nitrogen doping. And the last synthesis method is zinc doped black TiO2 nanoparticle. Is to degrade pesticide using 300 watt visible light, and it shows significant effect, which removal of 95% using optimized 2 mole % zinc doped black TiO2. To conclude, the investigation on black TiO2 production and photocatalytic performance taught me a lot. First conclusion is to select the right synthesis process affect the black TiO2 nanoparticle shape and crystal structure. The different synthesis processes produce different morphologies and crystal structures, which affect the photocatalytic activity. The second conclusion is black TiO2 outperforms white in photocatalysis. It produces hydrogen gas and removes dyes better. Black TiO2 is potential for environmental cleanup due to its enhanced activity. The third conclusion is black TiO2 reacts to visible light, unlike the UV sensitive white TiO2. This increases the black TiO2's photocatalysis applications and solar energy efficiency. The fourth conclusion is the variable crystal structures and morphologies of black TiO2 from diverse synthesis techniques make direct comparison of photocatalytic activity difficult. Different synthesis methods have pros and downsides. Recommendation for future. The first recommendation is to use doped black TiO2 to photocatalyze pharmaceutical waste or antibiotics, incorporating noble metals like palladium, osmium, iridium, platinum into the black TiO2 may improve its photocatalytic efficiency. Recommendation 2 is to study how black TiO2 improves photocatalysis. Understanding black TiO2 surface responses can help improve its use. The third recommendation is to study how synthesis circumstances affect doped black TiO2 optical characteristic. We can optimize the material optical characteristic and photocatalytic efficiency by varying synthesis conditions. Thank you for listening.